Let's look at our code, Ryan. So why did we do the if check? Do you mean right here? What seems to work without it? Get neighbors at very least. Well, I mean, it would work, but it would have bad data. And then I'm actually looking at it. Our little built-in tests here don't have a test for that. On line 33, yes, that's an error. Thank you. Good eyes, Seth. Yeah, sometimes there is, sometimes there isn't. Sometimes you've got to write it on your own. Users will always find your edge cases. That is definitely true. All right. So which one do you want to do first? The breadth first or depth first traversal? Dealer's choice. They're basically the same. So yes and no, Jonathan, and we'll talk about that. That's an excellent point, is they are very close to the same depending on how you implement them. Depth first because of recursion. All right, that's fair. Let's do that. So let's start with the regular one. And this, if nothing else, this is what I want you to memorize, because it will serve you well forever, which is how you do one of these. And that is create a queue or stack as appropriate. Then put the starting point in that. While there is stuff in the queue or stack, pop the first item, do the thing. What is the thing? Oops. And with our method, there's a if not visited. Whatever it is you're doing, that could be printing it, that could be calling a function on it. If you're searching, stop. Whatever you need to do, you do it there. Then, for each edge in the item, add that edge to the queue or stack. If you can memorize this, you can always do this problem. And this will be in your, sorry about that. That will be in your toolbox. All right. Gracias. All right. So I'm going to put this pseudocode here for both of them. All righty. So for a depth first traversal, what are we going to use, a queue or a stack? Stack. Yep. Are we going to name our stack S? But did we discuss about a reason why it might not be a good idea? Yep, Seth has it. Seth remembers what we learned from last week is that the Python debugger has a bunch of single character shortcuts built into it that get confused with and override one letter variables. So I have learned in Python at least, and in general, it's better to write your variables out anyway. I have learned that it's better to write it out. So for stack, we can write out the whole thing. Yeah, and IntelliSense makes single letter variables less meaningful and useful anyway. We're not getting paid by the character anymore. So stack equals, I have a stack imported. That's nice. What might I want to do right now? I'm importing something. What's probably a good idea? Let's take a look at that. We've got a queue and stack. So here's the stack here. So first thing, my linter is super unhappy about this file. Should I fix that? Why or why not? Your OCD says next, nope, because of team. I'm with Lloyd. This is one of those things that can become acutely political despite people's best intents, or again, because people. So there's a couple of things here, and I would hope that that whatever working environment that you're in, you know the answer to this comfortably and confidently, and you can ask someone if you don't. But I want to share a couple thoughts on this, and that's why I actually have left this like this. The linter is unhappy because of the number of blank lines. So a lot of things could happen. This file could have come from an external source, or it could have been written by a colleague before we changed what our style guide is. Could have been written by a colleague who did not follow the style guide. But under most circumstances, absent some kind of outside direction, it's usually seen as petty and invasive and very frustrating for someone to go into a document that another coder has written, might be maintaining, and go in and just change a bunch of stuff, particularly stuff like style. That's kind of rude. Now, there could be exceptions to that. We could be in an environment where we have changed, we've made an organizational shift, and we've changed from one style guide to the next, and it could be a standing order if you change a document updated to the new style guide, in which case you should change it. But we're not changing this one. And the other thing that I've learned is that that doing this kind of stuff, there's a category of things, and it depends on where you are and what you're doing, what this category is. But it's like being really good at PowerPoint or being really good at Excel or typing really quickly. And if you're good at that and start volunteering to do it, what do you think's going to happen? You're going to get asked to do it all the time. And now it depends. If you're doing commission sales and your boss offers you flat rate at your benefit rate to put together a PowerPoint, and yeah, I'll do that. But if you'd rather be solving cool problems and writing cool code, then don't be known as the person who's super efficient at going in and fixing formatting. But also don't be the person who won't do it, because then people just think that you're a jerk and you're arrogant and won't like you either. So find the middle ground, but be deliberate in your decisions. Yeah, Josh, my personal opinion on this whole debate is I'm personally annoyed that programming languages allow for variations. And I don't think it should compile under this state. But again, that's also in part my background where, I'm used to a C# and C++ and languages where anywhere where a red squiggly line screws up, it's not going to compile. So, yeah, so do it in wine the whole time. Exactly. Luis is going places. All right. Anyhow, other thing that we're looking at, why is this Q class suboptimal? What have we learned in our computer science education that makes us realize that this is not the most efficient way to do it? List versus linked list. Popping the O of N. Thank you, Jonathan and Matt. Are we going to fix this right now? No. Why not? And what are we going to do instead? Discussion with the team, absolutely, Seth. Make a note, Jonathan. That's a good idea too. Import the Q from the default Python libraries. We could do that, Catherine. That is probably a more top of the list thing. But didn't write it. Let's talk to our teammate. Let's ask about it. Let's bring it up. And really, it depends on the overall problem. And in this case, when would this be a real world problem? A large number, a large N, and when would it be worse? What type of graph would make it worse? When would you end up with lots of items in the queue? Because this is only bad if we regularly have lots of things in the queue, right? So we're narrowing in, Lloyd and Jason. And Eric's closed us, and Catherine as well. So a dense graph. If we have a very large, very dense graph, that we're going to have lots and lots of things in the queue, and we need to process things all the time, this is a place where we could optimize. But when do we optimize? At the end, or when you have to. Only when it's needed. Because otherwise you'll never get anything done. You want to strive to be efficient by your nature, but only optimize when need be. Yeah, so the last step of our problem solving framework, of UPER we call it now. We have a programming specific one, Lloyd. So at the end, now that's quite a graph. The backbone of the internet. That's just the backbone. That's just the major connections of the internet. All righty. So put the starting point in that. So stack dot push our starting vertex, then while stack dot size is greater than 0, pop the first item. So vertex is stack dot pop. If vertex is not invisited, what is that? What did Brian forget to do when he was writing his pseudocode that we need for this that we don't need for a tree? Keep track of where we've been. Make a set to keep track of where we've been. All right. Let's do that real quick. Visited is set. Could we use a list or an array for this? Yeah. Unless we have a gigantic graph, will there be any meaningful difference between using a list for this versus using a set? For our data sizes of like 7, is there going to be a real world measurable difference in the runtime for this? Nope, not at all. So why are we using a set? Because it's better, and we know how to. So again, we want to strive to be efficient, but hold off on optimizing. But this little line right here, being in a whiteboard interview and saying out loud, I know for such a small sample size, we could probably just use an array here, but a set will be better because it's O of 1 lookup and it doesn't have duplicates, so it's more space. It's more space efficient as well. You get bonus points for that. Is a common pattern to keep auxiliary data structures and/or helper functions in a utility file? Yeah, it's very common. With a lot of programs, particularly programs doing more complex logic, you end up with just a subset of classes and functions and methods that aren't really big enough or complicated enough to justify their own file. And so you just make a utility file or a helper file. That's a pretty common thing to do. And they tend to become useful. Like a few years ago, I worked on a game, for example, and I made a helper function originally just for one particular item in the game that I wanted to be random colors, but I wanted those colors to be bright. And if you just randomly generate RGB or hex code, they on average tend out to be kind of drab. So I made a helper function for that, and I stuck it in my helper functions, and then it ended up being useful for everything everywhere. Oh, the title screen. The title should be a random color every time. Let's make it one of those bright colors. And so you'll just build up a set of useful things. You know, because the stack or queue are useful for our traversals here, but they might be useful for something else. And they're not directly related to this, so we compartmentalize it. Alrighty. So we have our visited set, we have our while loop. And again, don't beat yourself up when you do stuff like this. I've been programming for a long time, and it's just Tuesday to conflate one method of doing things and the other. And I've still got the one where we did this for trees in my head, where you don't need this because in a tree, you can't find somewhere you've been before. Or if you do, you've done something wrong. All right, so if not visited, how do I know if I visited it or not? Easy, if vertex not in visited. Then we do the thing. What is the thing for this one? Print it. All right. And add it to visited. So we've got another line that we need to add to our pseudocode. Yeah, I'm going to put this in the notepad as well. All right. If not visited, do the thing, add it to visited. So visited dot add vertex. And then for next vert in self.getNeighbors of what? Whose neighbors do we want? Our vertex. Add them to the queue or stack. So next stack dot push next vert. All right. Let's save this. Fix the extra space. All right. CD into graph, or CD into projects. Graph. Python 3, graph.py. All right. Well, a lot of things aren't working, but one thing is. The first thing is, the second thing, and all right, what's going on here? Have we passed? Have we failed? I don't know. What can we do? This test is confusing me. Yeah, let's add some stuff. So let's add a line, printing graph.vertices. Then here, print running BFT. Print running BFT. Print running DFT recursive. All right. Print running BFS. Print running, keep missing my shift key. DFS, and one last one. All right, let's save that. Let's run it again. Okay. So running BFT, it didn't do anything. Running DFT. All right. Wait a minute. So it is running this, and it went 1, 2, 4, 7, 6, 3, 5. So that's this one here. But why are there different orders? What gives? Unordered sets, right? But what does that mean? Which one of these is the solution? And when I ask you questions like which one of these is the solution, I'm usually giving a hint. Because what do depth first and breadth first searches and traversals provide us? Are they going to tell you what the answer is? Nope, they will tell you a answer. And there could be more than one, right? We go, we make a very easy graph. So this is our graph. We're going to start here, and then going depth first. We're going to go to here, and then keep going. And we're going to go to here and keep going. And we're going to go to here, and then we're going to look and say, nope, I don't need to go there. I've been there. Or we could go the other way, and we could end up going this way. And both of these are valid. And what are these things called? What do you get as the result of a breadth first traversal? I mean, sorry, a depth first traversal. What is the result of a depth first traversal? It's a minimum spanning tree. It's a tree. And what does it do? What does a minimum spanning tree do? Gives you a solution of the shortest number of connections between all of the nodes. And does anyone know what the total set, oops, wrong button. Does anyone know the name of the total set of all of the minimum spanning trees for a particular graph are called? Minimum spanning forest. Sometimes programmers are funny. All right, let's get back to this. So, I know, Lloyd, you want to go and get to recursive, and we will, but I'm going to skip that for now because we've got this one done. We've got this one working. What does that mean for all of the rest of these? A forest is a collection of trees, Amir. Like a shrub. So if I want to do breadth first, what can I do? Copy paste. Yep. Remembering that copying and pasting is a terrible idea that often adds in very difficult to find and debug problems. I'm going to do that very carefully. Change that to Q. Change that to Q. Q dot, what do we do to Qs? Well, let's take a look at util. We enqueue in our queue. All right. Visited is still a set, while queue size instead of stack size. Vertex is Q. Come on. Why is it? There we go. Q dot DQ on line 41. Thank you. All right, print the vertex, visited add vertex. Those are the same, but we're going to Q dot enqueue. Let's save it and run it. Oops, it's not called DQ because I spelled it wrong. DEQUE. That was a deck, which is a doubly ended queue, which is a whole nother can of worms. DQ. All right, let's try that again. Let's save it so it runs something differently. All right. And it's working. Sweet. One very careful and important caveat to this that you may see and it may trip you up. What happens if I do this? What is the front of our queue? Well, we can take a look. So the front of our queue is 0. So what if I do this? You might see this. So what if I just look at it now and pop it out at the end? Will this work? Not quite, Jonathan. Look at the first item. Let's walk through it step by step. Let's look at the first item in the queue and give it a name to make it more convenient to access. Or here, let's even go further. This is really the way that you would see it. So if well, no. That's not the problem because we'll go and we'll say queue size is greater than 0. Yeah. So, oops, we don't need that. So if the first item in the queue is not in visited, it's not. We have not been to the first item at the list yet. Print the first item in the list. Add the first item in the list in visited. for each of the edges, add its edges to the back of the list, and then get rid of the first item in the list. This will work just fine. And you will often see the pseudocode of doing a breadth first traversal or search done this way. But what happens if you try to do a stack this way? If you try to do with a depth first? Catherine has it. It wouldn't work. Because what happens to the stack if you don't immediately pop out the top item on the stack? That's when we get the infinite loop. Because when we get down here, we're going to start adding items on top of that, and then we're going to take them off, and then we'll get back to where we started. So keep that in mind, that you can do change between one of these and the other by swapping a queue and a stack, but only if the queue is at the beginning and if you're popping from the queue at the beginning of the while loop. And I've gotten caught on that before and become very confused and frustrated. So keep in mind that that's a pitfall. All right, let's make sure it still works. It is. What else should we do? We've got some code that's running, it works. We have not done in a while. Commit. Let's take a moment to do that. All right. So again, Lloyd, I apologize. We're going to skip the recursive one for a moment, not because it's harder, but because it's just different from what we're doing. What can I do for the search here? Reuse a lot of the code. So let's grab our breadth first search code. And remembering that copying and pasting is a terrible idea. So breadth first search, I'm going to paste it here. I think I got too much. What did I do? I don't want that. See, I've already confused myself because by copying the comments, I could have then followed the wrong spec and repeated myself. All right. Now I grabbed the wrong one. See, this is why. I swear I'm not doing this on purpose. But this is why copying and pasting is so dangerous, particularly if you're me. All right. Depth first traversal. We'll copy depth first traversal. And paste it into depth first search. So if all we wanted to do is use a depth first search to find a vertex with a certain value or something like that, what would we do? Stop popping, right? So where would we change things? What is the thing? It would just be what? If instead of printing, we're going to do something else. If vertex equals what? What extra parameter do we have up here? our destination vertex. If vertex is destination vertex, do whatever the thing is. So we're going to move that to there. And then what do we do? We return. And then possibly return the thing, right? So if we were just searching for a vertex, then it would be pretty easy. We would just return the destination vertex that we've just found. But that would be kind of silly because we usually don't need just the vertex itself. In this case, we want the path to it. And one clever way that we can do that is to make it as we go along, which is what I'm going to show you how to do. So instead of enqueuing the starting vertex, I'm going to start building a path. So let's put a note here. We're going to, oops, or in stack, is that the word? We're going to in stack a list to use as our path. All right? Then, instead of working with a vertex, we just have to change it so it works with a path. So our path is now whatever is the top item in the list. All right? Then, we still need our vertex because we're working with that. So what does our vertex equal? It's the last item in that path. Right? We're building a path step by step. So our vertex is going to be the last item in the path. If our vertex isn't visited and it's the destination vertex, what do we do? The thing is just to return the path. We're done. We found the vertex we're looking for. We've built a path to get there. And that works. Otherwise, same as before, we add visited to the vertex. And then we need to do one more step down here, right? Instead of adding, because we're working with a list, so we need to add the vertex to where? Add each new vertex to the end of, because we don't want the vertex itself, we want a path to that vertex. So we have a path to its parent. So we just add this to the end. All right, so let's do that. But we have to do something else. We can't just say, oops, path dot append next vert, right? Why can't I do this? What's going to happen? What very confusing bug will this cause? Yeah, Alex has it. It changes the original path variable. And then I'll push it. So what are we going to end up with on our stack? As this loop goes through and it keeps changing the original path vertex, we're going to end up with a stack full of copies of the same thing. Because what? Lists are objects, and objects in Python operate under what principle? If I say path2 equals path, and I say path2.append test, say path1 equals path2. What's going to happen? What is this going to resolve to? This is true. Or I'm sorry, path equals path2. This is true because Python is passed by reference. Objects are passed by reference, which means when you do this assignment, you're not creating a new one. You're just saying this is another name for the same thing. Which is actually what this does here too. So give me a new name for stack sub-0. So I don't have to type stack sub-0 all the time. Although pop also gets rid of it. So what we have to do here instead is we have to explicitly make a copy. Make a note here. Copy path to avoid pass by reference bug. Also, a word of advice to keep in mind. If you're programming and you're printing things out line by line, and you feel that you are going insane and that what you're seeing can't possibly be true because you're explicitly telling it to be something different, and you feel like the world is just spinning, it almost certainly means that you have a pass by reference versus pass by value bug. Yeah. Well, I'm sure, and there's a good chance that that's what the bug was. So what we need to do is we need to say new path equals list path. And so what this does is it makes a copy rather than reference. And then on new path, we'll append the vertex. And then we will push the new path. Lloyd, if you're debugging and you're going and you're like doing something like path.append 1, print path, path.append 2, print path. And that is making you, and that is not printing out 1, 2, 3, 1, 2, 3, 4, like you're telling it to do. And you feel like you've gone crazy and what's happening can't possibly be happening. It very often means that you've confused pass by reference with pass by value. And you think you're working on a copy of something, but you're actually modifying the original. All right. So now we push our new path. And so what is this going to do? Then, what does this code do in terms of paths? Right, it's going to do new path, but what's actually happening here is we're building lots of different possibilities because it's called stack. Thank you. Thank you, Tanya. Sorry. And thank you, Will. But what we're doing here is we're building a bunch of different possibilities of paths until we find the right one, and then we're returning that one. All right. So let's save this and run this real quick. Running depth first search. Wow, good call. Nice little bug right there. Next vert. Thank you, George. That is an excellent catch. We want to make sure we're appending the right thing to the new vertex, not the old one. Let's try that again. Running depth first traversal. Running depth first search. 1, 2, 4, 7, 6. So going back to the question that we had earlier, I think it was Will's question. Apologies if it wasn't. But why don't we have a test file for this in a test suite? Why aren't we using our normal method for testing this? Because there's multiple right answers. So sometimes it's just simpler and easier to do things the primitive way. We get the same result. All right. Let's do this. We're running a little late, but we started a little late. So let's do the breadth first one. And then I want to whiteboard this, but we'll take a break first, and then we'll get on to solving problems. And I haven't forgotten about the recursive ones. We will get to those too. Yeah, today's a weird day, so even though the rules say I'm not really supposed to, I think we can get away with it. Actually, let me do the. I'll share the code at the break. Because we're going to make our breadth first search. Which one am I going to copy and paste and then say my mantra about why it's a terrible idea? To get to breadth first search, am I going to copy my depth first search or my breadth first traversal? Could do either, but I think this one's easier. I think the search and changing it from a stack to a queue is easier and less risky. So breadth first search, I'm going to paste that in. And what do we change? Q. What am I hitting that it doesn't like that? Q.enqueue. Visited is still a set, while Q.size is greater than 0. Our path is Q.dQUEUE. Vertex is still the end of the path. These are still the same. Still the same. Still the same, still the same. Just Q.enqueue, our new path. So let's save that. And run it. Running breadth first search. Oops, we've got an error. Done it again. Need a capital Q there. Fix that so the linter's not mad at me. Thank you, Seth. Depth first search, no, that's still expected. All right, here we go, running depth first search. So breadth first search and depth first search are both working. All right. So let's draw it real quick. We don't have to go through the whole thing, but I found that for me at least, drawing what we were doing here helped quite a bit. So let's look at this. Let's look at this image. Oh, nope, that one's not going to work. Let's try this one. Here we go. I'm not sharing my screen again. All right, so we've got that. Let's use our powers of developers to make this more useful and make the background be white instead of black so we can draw on it. All right. So this is the same as before. We've done this a bunch of times, right? The only thing that's different, pick your numbers. Where do you want to start and where do you want to end? Should we take a break now? All I need is 2 numbers from you. 1 and 5. Thank you, Luis. So we're going to start at 1 and end at 5. All right? So that's the other question, Lloyd. Do you want to do depth first or breadth first? Both are being done the same way. All right, well, Lloyd mentioned depth first, so let's do that. But we could do this with breadth first also. So depth first search, we have what? A queue or a stack? Stack. Sorry, Will. All right, so we're starting at 1. Oops, I need my mouse. Close that, get a little more space. So we're starting at 1 and going to 5. So what am I putting into my stack? I'm close. I'm putting a list with 1 in it in the stack. All right? Then what's the next step? Top of the while loop. We pop the top item in the stack, right? So we take our 1 out and we look and we find 2. Well, let's look at, hold on, real estate is going to be a challenge, but I think we can do this. Let's put this over here. Oh, nope, definitely can't do it that way. Let's do the other way. Let's put this over here. We can get rid of that. Move that up, get rid of that for now. I'll queue, while stack. All right, so while stack is 0, greater than 0. We've popped the first item. And then our vertex is 1. All right, so we're working with 1. 1 is not in visited, so we need our visited list up here. All right, 1 is not our destination, so we're not done. We can skip this part. We'll add 1 to visited. Then, what do? For each vertex in 1's neighbors, so 1's neighbors are going to be 2, 7, and 4. What do? We make a copy. Does this not let me copy and paste? I guess we're going to have to do it the hard way. So we make a copy of our path. Path is a list because we are pushing right here. We're pushing starting vertex in a list. And then when we pop it out, we get a list that has starting vertex in it. Excellent question, Josh. Yep, no, that's why we're doing this, because it's so easy to miss. I was very confused by this method the first time I saw it. All right, so we're making a copy of our path down here. We're appending our next vert. So we'll append 2. And then we put that on the stack. All right, let's make our stack a little wider so these things can fit. There we go. All right. Then we go to the next set of neighbors. All right. So we go and we make another copy. What are we drawing? There we go. We make another copy of our path list, which already has 1 in it. And we append 4. Why did I append 4 and not 7? What reason did I have for that? Yeah, it's unordered. It's arbitrary. We have no idea what order this is going to happen in. All right. And then we do the same thing for 7. So we make a copy of our path with 1. We add 7 to the list. We enqueue it. Then we're done with this iteration of the while loop. So we start again. So these go out of memory. We go back up to line 145. Path equals stack.pop. So we pop out the top item in the stack. Might grab my large awkward comma there. So it's 1, 7. What is vertex equal to? Seven, the last item in the path. So our vertex is 7. Vertex is not in visited. 7 is not in our visited list up here. All right. 7 is not the destination vertex. So we add it to the list. And we go through and we add we make a copy for each of 7's neighbors. So we go 4 and we say, oops, that's really bad. Let's see if we can get this under control. We say, we copy our path, right? So our path was 1, 7. And then we add 4 to it, one of its neighbors. Then we NQ that, or put that in the top of the stack. And then we look and we see 7 has another neighbor that's 6. So we make a copy of our existing path, which is 1 and 7. And then we append 6 to the end of that. And we put that at the top of the stack. And then we see that we have another neighbor called 5. So we copy our existing path, which is 1 and 7. And we append the 5. And we put that on the top. And then we're out of neighbors. So we're done with this for loop here, the line 154 for loop. So we're done with the line 143 while loop, and we start a new one. Stack size is greater than 0. Those are out of memory now. Path equals stack.pop. So we pop that out. Vertex equals the end of this path. Vertex equals 5. And hey, what do we have here? If vertex equals destination vertex. We found it. So we return the path that we've built so far. And all of these other paths, all of these other potential options, we don't need anymore. They could be valid solutions. They could not be valid solutions. There could be many. Again, it's possible with a depth first solution that we went from 1 to 2 to 3 to 6 to 7 to 5. And that's every bit as valid. But we found our first valid path by using this method. And you're welcome, Luis. I hope that, oops, I keep hitting the wrong button. I'm sorry. Sorry. I meant to hit the annotation button. Now this is in the way. Zoom is very useful, but no matter what you do, that Zoom toolbar always ends up in the way. All right, let's break here. So actually, I am going to stop sharing again. Sorry about that. Let's break here. Please forgive me, Will. I know I've been toying with your expectations and your hopes and dreams. Let's take a break. Steve, if you could give us a 10-minute timer, and then when we'll come back, we will do the recursive ones, and then we're going to do our breakout room exercise. And answer any more questions that you have. See you all in a minute. All right, everyone. Let's go. Any questions before we finally get to recursion? And sorry, Lloyd, and thank you for your patience. All righty. Steve, I think you may be unmuted.
Oh, sorry about that.
All good? All right, so let's do depth first traversal recursive. Doing it with recursion. All right, so looking at this, what's the first thing that we need to do? What is a requirement for pretty much any recursive function call? What do you have to do? A recursive solution to a problem. Well, you need a base case, right? But before that, what else do you need to do? What does each call of the function need? What do you have to continue to pass in and return out if you're solving a problem with recursion? You need storage. You need the solution that you have so far. And for a function that is supposed to visit every node in a graph, you need the list of visited nodes. Visited, which the default will be none. And then, as several of you said, we need the base case. So if visited is none, what do we need? We need a destination will for the search, but for a traversal, we don't need a destination because we're going to go everywhere. But good catch. Jonathan, that is an excellent question, and led, if we had more time, I would go down this rabbit hole. But the reason that you can't say visited equals set here is because of the archaic details under the hood of the way how Python works. Is the set will get instantiated at compile, not at run, which means you will start to get really weird, crazy bugs. It's also a good lesson in why not to be fancy unless you're really sure of what you're doing. So there are some circumstances that'll work under Jonathan. It'll work the first time you run it. And you won't be able to see any errors. But then if you do two different tests with that first recursive, the first one will work and the second one will fail because it's using the same set as the first one used. It's a really weird edge case. And I could see it causing massive problems. So if visited is none, then we instantiate it. Dan, it should work the first time. But if you call it again, then it won't work. So if you do recursive twice, the same function call, both function calls will use the same set in memory. You won't get a new one each time. All right. Same as always. So we're doing basically the same thing that we've done before. We've created a set of things that we visited. We're adding the start vertex to where we visited. And then what do? For each child vertex in what? Self.vertices for our start vertex. If we haven't seen it before, what do? We encounter a vertex that we've never seen before. Oh, and we forgot to do one other thing. We forgot to do the thing, right? So we'll print our starting vertex. And if we have children, if we have edges that we haven't visited, what do? What makes this recursive? Self.bft recursive. But instead of our starting vertex being this vertex, it's going to be the child vertex. And we also pass in our current set of visited. That's it. So what did we learn about this when we whiteboarded this when we did traversals through trees? What is this actually doing? What does any recursive function call do? Visited, yes, .add, thank you. It creates a stack and it uses a stack. So that's why we can use recursion to do a depth-first traversal or search, but not a breadth-first traversal or search, because we are forced to use a stack because it's recursion. All right, let's test this. See if it works. This is DFT recursive is up here, and that worked just fine. So how are we going to turn a traversal into a search? We're going to copy it and paste it, and very carefully, because this causes lots of errors and bugs, modify it. All right. So for this, as someone had that, we also need the destination for DFS recursive. So we need, well, we need a few things, actually. We need the starting vertex. We need the target value. We need what we visited. And we need the path. All right, and I'm going to blitz through this because we are behind time, and I want you to get at least started on this exercise. So, same as before, except we've got a new base case. If path is none, we need to instantiate that as well. So visited equals our starting vertex. What do we do with path, though? Well, we add our starting vertex. Path equals path plus starting vertex. All right. We don't need to print anymore. Instead, what is our thing? If we found what we're looking for, if start vertex equals target value, then we return our path as before. Otherwise, for each child, if the child is not invisited, how do we call this? Well, we're building a path, right? So we need to say our new path is self.depth first search recursive with the child vertex as the starting vertex. Target value is the same. Visited is our visited. And path is the path. And then what do we also always need to have for a recursive solution that is returning a value at the end? If we have a new path, return it. Why do we need that if? And then at the very end, we return none. What is the if and the return none catching? What's possible? The target doesn't exist. All right, looks like we've got an error. Line 264, missing 2 required positional arguments. Because what did I forget to do? Forgot to give them a default. No biggie, we can fix that. We'll ignore the linter being unhappy about the long line for now. Run it, and here we go. All right, any questions? Just frustration, sorry, Will. Arthur, because actually this doesn't get involved in the homework. Yeah, because it's a weird day, I will go ahead and do that for today. But remember, normally the rule is that I'm obligated to follow is that you can always get your solution code from your team lead during your one-on-one. And we are not supposed to give it out otherwise, but because it's a short week and an odd case, we'll go ahead and do that for now. Okay. All right, so here's what we're gonna do for the rest of our time. We are gonna do breakout rooms for just a little bit, and that's just gonna run into lunch. And so at lunch, you're more than welcome to stop, or you can carry on with your group if you want, it's up to you. But I'm gonna give you an interview problem to practice. And then we'll do the solution for this. We'll talk about the solution for this tomorrow. But you will find that graphs problems are very common in interviews. They're favorite whiteboard things because anything that is a relationship can be described with a graph. And almost every problem involves things that are relationships. So I'm going to share this in the notepad. And I'm going to read it out and talk about it. What I would like you to do actually is work with this until you run into lunch. And then after lunch, try to get with your group and come up with a solution for it. This is good practice. The homework problem is also good practice. But do this one as a group first. I'd rather you do this one and work on it in a group and not quite get the solution or not get the homework problem done. Then not do this one. Okay. Amir, the reason why the queue is suboptimal is because it's O of 1 to take the front item out of a list. I mean O of n, not O of 1. It would be O of 1 to take it out of a linked list, but it's O of n to take it out of a Python list. But again, with the short list, it doesn't really matter. All right, so look in the CS24 notepad. The problem to solve is given two words, beginning word and end word, and a dictionary's word list, which I'll drop in here in just a second. Return the shortest transformation sequence from begin word to end word, such that only one letter can be changed at a time. Each transformed word must exist in the word list. Note that begin word is not a transformed word. Return none if there's no such transformation sequence. And then there's some data and hints in here. The biggest hint that I have for you with this problem and for many graphs problems that we're going to introduce now to try and let you figure out on your own, and then we'll demonstrate tomorrow, is that you don't always have to build the entire graph to solve a graph problem. Sometimes instead of building the whole graph, it's a lot more efficient to just compute the graph for the particular spot that you're looking at. So I'm going to break you into breakout rooms, and I'm going to drop in the channel, the word list. I will keep this running throughout lunch. You do not have to work on lunch, but I would ask you to get with your groups after lunch and work on this problem for an hour before you move on to the homework. Any questions? Oh, I'm not looking at the right thing to see the questions, am I? Doesn't look like there are any questions, so I am going to open up the breakout rooms, and then I will drop that file in the notepad. If you have any questions, I'll be checking Slack throughout the next couple of hours, so please don't hesitate to ask.